Now let's see this Newton's method in action. First we're going to approximate an x-intercept. So let's, to 4 decimal places, approximate the x-intercept for f of x equals x to the third plus x squared plus 1. Use x sub 1 equals -1 as your initial approximation. So this problem tells us a couple things. What we want is we want to actually nail down the x-intercept of this with a particular precision. We want it correct to 4 decimal places, so that'll be something to watch for. The other thing that's nice about this problem is they give us an initial approximation to work with. That way we're not going down a rabbit hole of trying something to find out it wasn't a good approximation to begin with. Okay? So let's get started here. X sub 1 equals -1. And we know to get subsequent x values, so just a reminder, to get subsequent x values, x sub n plus 1 will equal the previous x value minus f of the previous x value divided by f prime of the previous x value. So if we want to use this formula, we have to have a previous x value. Well, that's x sub 1. That's going to be our initial x value. We have to have the function. Well, that's this function here, right? We have our initial x value. That's x sub n, or x sub 1 initially. And we have to have our f prime function. So we don't have that yet. So let's go ahead and find our f prime function, which will be 3x squared plus 2x plus 0. So we don't have to write the plus 0. So what we're using in this problem is the formula x sub n plus 1 equals x sub n minus the fraction. On the top, I need to plug x sub n into my f formula. So my numerator is going to be x sub n cubed plus x sub n squared plus 1. My denominator, I need to plug x sub n into my derivative formula. So here it's going to be 3 times x sub n squared plus 2 times x sub n. Alright, so I'm going to talk you through the idea of how to use the calculator to do this, okay? And then I'm going to cut into this video and I'm going to show you how to actually do it on my scientific calculator. So the first thing you would do if you're using a scientific calculator with memory is you would store this x value into your x variable, or whatever variable you want, okay? And then you would calculate, so you don't type x sub 2 equals, you're just going to type this formula into your calculator. So x sub 1 minus f of x sub 1 over, sorry, not f of, I need to use the formula we came up with. I have to actually plug x sub n into the formula, so in this case it's going to be x sub 1 cubed plus x sub 1 squared plus 1 over 3 times x sub 1 squared plus 2 times x sub 1. So you're going to type this into your calculator, but you're not going to use x sub 1, you're just going to use the x variable from your calculator. So every place I've got an x sub 1 here, you're going to literally use the x variable on your calculator. So you're going to type that in. And when you do, which by the way, x sub 1 is -1, so that's what's actually plugged in for all of these, right? You're going to get, and I've got it figured out already, you're going to get -2 as your second approximation. Now to get x sub 3, you need to store this new x value in for the x variable on your calculator, and then you're not going to retype this formula. You're going to just use your up arrow to go refine the formula in your queue of entries, of inputs to the calculator. So you're going to go up here, you're going to hit enter, and recalculate the value of this formula with your new x value, -2. Okay. Now, if you're not following along with this, that's okay. I'm going to show you precisely how to do it. I'm wanting to walk you through it as we're doing the calculations. So if you do that, your x3 value is going to be -13/8, which let me write that as a decimal here to get an idea. -13 divided by 8. Oh, well, that's -1.625, okay? Now let's keep in mind what we're doing. We went from -1 to -2. Those are pretty far apart still if we're wanting to get our precision to 4 decimal places, or our accuracy to 4 decimal places. So you can see -1.625 is a little bit closer to -2 than we were before, but not close enough. So we need to keep going. So now we're gonna store this new value in for x on our calculator. We're going to retype the same formula by using our up arrow to go find it. And if we do that, our x of 4 is going to be -1.4857,859,53. Okay? So now we didn't deviate too much from our previous approximation, but you get the idea now. We're going to store this in for x, go re-enter our formula, and our x of 5 is going to be -1.46595592. Okay? So what we're looking for an answer that's correct to 4 decimal places. So we're looking for the 4 digits after the decimal to stop changing. Once those stop changing, we know that those 4 are correct. And we can see we're not there yet. Right now, our last 2 approximations are only equivalent to the -1.4, and then they deviate in the 100th place. So we need to keep going through this process, and you could see if you didn't know a shortcut on your calculator, this could really be a nightmare because you'd have to type this formula in over and over again with these nasty numbers. Okay, so understanding the shortcuts is going to be critical to doing this efficiently. So x of 6 is -1.465571,375. Well, now we're a little better. Now our approximations are correct out to 3 decimal places, but not to 4. So let's do another iteration and see if we can get them equal out to 4 decimal places. So applying the process again, we get, sorry, my pen is not changing color. There we go. X sub 7 will be -1.465571,232, and now our last 2 approximations are equal out to 4 decimal places. So if we want to approximate the x-intercept of this function to 4 decimal places, the answer is -1.4655. Notice I didn't round my 5 here up to a 6 because I had a 7 after. I want the 4 digits after the decimal place to match the actual x-intercept of this curve. Okay? And this is the type of thing that computers do to actually find x-intercepts or solutions to equations. Okay? Now, there may be more efficient techniques than this one, but this is an excellent introductory technique for a basic calculus student. Okay, so it's really fascinating that you can do this just with this derivative idea. Okay, let's cut away now, and I'll show you the video of how to do this on your calculator, and then you can work with me on the upcoming examples. Okay, so now I'm going to show you how to use your scientific calculator to do these Newton's method calculations pretty quickly. And we're going to use the memory on your calculator. Now here's my favorite, so far, my favorite scientific calculator. It's a TI 36X Pro. It works really well, and you'll see why I really like it for this application. Now, any scientific calculator that can store into a variable will work just fine, should work just fine. So let's start with that first example, and we need to store our x sub 1, which was -1, into the calculator for the variable x. So I'm going to use the store button down here and the X button right here. So I'm going to type -1 store X and then hit enter. And so that has stored -1 into the X variable on this calculator. Now I have to type my formula to calculate the next approximation. So in this case, we have X minus the fraction, so I'll hit the fraction button. And on top we have X to the third power, hit my right arrow, and do plus X to the second power, plus 1, so that's my numerator. On bottom I've got the derivative of that, which is 3x to the second power plus 2x. And now when I hit enter, what it's going to do is it's going to calculate the value of that formula using -1 as the x value. So I'll hit enter, and -2 is the next approximation. So that's the hard part, is typing all that in once. Now it's really easy, because -2 is the value that the calculator is holding. I want to store that as my second approximation. So now I go directly to, while -2 is displaying on the screen, I hit my store button and I hit X, and now it's going to store that -2 into the X variable. So I've got a new value in there. And then rather than retype the whole formula, I'm going to hit my up arrow to go back to my formula, hit enter to copy it, and now it's waiting to recalculate that formula with the new value of X. So I'll hit enter again. And you can see that we get -13/8 there, which is the next approximation. Now we just rinse and repeat over and over. So store that value, and for X, hit enter. Hit the up arrow to go grab your formula and copy it, hit enter. Calculate the value of that formula, hit enter. And you get the next approximation. Now we want to store that for X. So I hit store X, enter, up arrow to my formula, right there, hit enter to copy it, and then enter to calculate it. And you can keep going and keep going and keep going to get better and better approximations. Now, that is the fastest way I have found to do these types of problems with a calculator. I don't have to type in any of the values except for the very first one, and I just have to type the formula one time. So, regardless of what scientific calculator you have, even if it's not the TI, which I like because the variables are right here all in this button. You've got X, Y, Z, T, A, B, C, D. You could use any of those variables with this one button. X is the first one if you hit it once. If you hit it twice, you get Y. If you hit it 3 times, you get Z, etc. You can cycle through your variables. On other calculators, you may have to hit alpha and then a variable button to access the variables, which works just fine too. It's just a different workflow that you have to get used to. So I hope that helps. Try the rest of the examples along with me and see if you can figure out how to do this on your calculator. Alright, so I hope that helps. I hope you have a calculator that has memory of some kind, and you can adapt that technique to whatever calculator you have. I really like the TI-36X Pro, but Casio makes a couple good ones that work similarly. They're the FX115 ES Plus. That's a good one as well. So anyway, hopefully you have a calculator you can do that with. Let's do our next example though, okay? So our next example, let me flip the page here. Let's use this to approximate a cube root. You can do this with any root, but let's approximate the cube root of 30 correct to 8 decimal places. Correct to 8 decimal places. Alright, so you may be wondering, well, Newton's method is to help approximate x-intercepts, and it is, but you can think of x-intercepts slightly different. For example, with roots in particular, if this is our x value, our x-intercept, and I cube it, right, x cubed will equal 30, right, because if I cube the cube root of 30, I get 30. And if I subtract 30 from it, x cubed minus 30 will equal 0. And this is kind of really important. So x cubed minus 30 equals 0, if I can find an x value that makes that true, then that x value is also an x-intercept of this function f of x equals x cubed minus 30. Because to use Newton's method, you need a function. And in this problem, you can see there's no reference to a function, so we have to create it ourselves. Now, if you think about, now let's go backwards. If I ask you for the x-intercept of this function, the way you would do it is you'd plug 0 in for y and solve for x, right? And you could see that if you did that, you would get the cube root of 30. So the cube root of 30 is the x-intercept of this function. Now, that's easy. We know that's the x-intercept. But what we want to do is actually find the decimal representation of this correct to 8 decimal places. That's where Newton's method comes in handy. So, if we want to use Newton's method, the first thing we need is an initial approximation. We need an x1. So what's a simple number that we know is pretty close to 30, or pretty close to the cube root of 30? Well, we might say 3 is a good approximation because 3 is the cube root of 27, which is close to the cube root of 30. So that might be a good initial approximation. So we've got that. Now, if we want to use our formula, x sub n plus 1 equals x sub n minus f of x sub n. Well, here's f of x. So f of x sub n will be x sub n to the third power minus 30 over the derivative, so f prime of x would just be simply 3x squared. So on the bottom, we need to plug x sub n into the f prime formula, so we'll have 3 times x sub n squared. And so this is the formula we're going to use in our calculator over and over again. So I'll kind of walk you through it. I'm not going to show you the calculator process again, but I'll talk you through it so you can try it yourself. So first thing you need to do is store this for your x value. And then you're going to type into your calculator the formula x minus x cubed minus 30 over 3x squared. And feel free to pause the video while you type that in once. Once you type that in and hit enter, it's going to give you your x sub 2, which I've got here as 28/9. Okay? Once you've got your 28/9, you're going to store that in for x, and then you're going to not retype this formula. You're just going to use your up arrow to go up, select it, and re-enter it, and hit enter, and you'll get your x sub 3, which is 3.107,237,339. Okay? Then you're going to store that for x, because that's your new x value. Then you're going to use your up arrow to go enter this formula again, and you're going to get your x sub 4, which I have as 3.107,232,506. And remember, we need this correct to 8 decimal places. So we're looking at 1, 2, 3, 4, 5, 6, 7, 8, out to there. Okay? So we're not there yet. So let's keep going. Store it, re-enter your formula. In x sub 5, I got to be 3.107,232,506. I got the exact same thing that I had for my previous, and if I look at 8 digits, 1, 2, 3, 4, 5, 6, 7, 8, there they are, and they match the previous 8 digits after the decimal place. So the cube root of 30 is approximately 3.107,232,50. And it would be interesting, type this into your calculator, raise it to the third power, and see how close you are to 30. I bet you're pretty close. Okay? Now, let's talk more about this root business, for example. How do you take a root and create a function out of it? Okay? It's actually pretty simple. So let's walk through that. I'm not going to do another full example of that, but let's say you wanted to approximate the fourth root of 90. Well, if you raise that to the fourth power, you get 90. And then we know we need 0 on one side, so we're going to subtract 90 and have x to the fourth minus 90 equals 0. This guy is the function we want to use because to find the y-intercept we need this to be 0. So the function in this case is going to be f of x equals x to the 4th minus 90. And it's that simple. What if we wanted to approximate the 6th root of 130? Well, then if this was x, we'd raise it to the 6th power, and that would be 130. Subtract the 130, and that would equal 0. Thus, the function we would want would be x to the 6th minus 130. So you can use Newton's method to approximate roots of any kind by turning it into the x-intercept of a function. Okay. Now let's do one last example, which to me may be the coolest application, because students are always asking, how do you solve this equation? How do you solve that equation? Well, solving equations is difficult. And really, how do computers do it then? Well, they approximate. You know, when your calculator gives you an answer with all those digits, you have to understand that's an approximation because there's more after that. So your calculator doesn't care what those other digits are because it only has to show you so much. Okay, so that's what computers do. So let's say our next problem. Let's use x sub 4 from Newton's method with x sub 1 equal 4. So use x sub 4 as an approximate root. That just means solution, by the way. Approximate root of the equation natural log of x equals 1 over x minus 3. Let me fix that so you can see it all. Okay. So we want to use Newton's method to find the fourth approximation with x sub 1 equals 4 to get a solution to this equation, an approximate solution. Okay. So how do we take an equation and turn it into a function? Same idea. Get 0 on one side. So this equation is equivalent to, well, if I subtract the fraction 1 over x minus 3, then I have the natural log of x minus 1 over x minus 3 equals 0. And the key is getting 0 on one side because that's going to identify that what you have then is this function, the natural log of x minus 1 over x minus 3. And you know what? Because we know we have to differentiate, you might find it useful to rewrite 1 over x minus 3 as x minus 3 to the negative first power. Okay? So that's how you create your function. Take what you have, get 0 on one side, and then what's on the other side you want to call your function. Because remember, you're finding x-intercept and you want this to be 0. Okay? Now, to use the formula to run through the iterations on your calculator, we need f prime of x also. So we have to differentiate. The derivative of the natural log of x is 1 over x minus, here we have a little chain rule. So first we deal with the power. So we're going to bring the exponent negative 1 down to the front as a coefficient. And then we have minus negative 1. So that actually turns into a plus. X minus 3, and the power goes down by 1 and turns into negative 2. And then we apply the chain rule and we multiply by the derivative of what's inside. The derivative of x minus 3 is 1 minus 0. So the derivative is just 1. So we don't really have to multiply by it because it doesn't change anything. Okay? So this is our derivative function. Alright, so here we go. X sub 1 equals 4. X sub 2 is going to be our formula. So let's run through this process again. Store this in for x. Type your formula. So let's write out the formula. X minus f of x. Well, f of x is this guy, so type that in. So we've got the natural log, and your calculator might force you to put parentheses around the x, minus x minus 3 to the negative first. Okay, so that's f of x. On the bottom, we need f prime of x. So if you don't like the fraction, you can always call 1 over x, x to the negative first. But you have 1 over x plus x minus 3 to the negative second. Okay? So this right here, you're going to type that into your calculator, and that's going to give you your x sub 2. And what I have for x sub 2 is 3.690964,511. And this problem told us specifically to use x sub 4. It didn't specify a precision for our answer. It specified which iteration do you want to use, and that's x sub 4. So now we'll store this new approximation in for x. We'll go back up, enter the formula, hit enter, and we'll get x sub 3 to be 3.750726,187. Okay? We'll store that to be our next approximation. Go back and re-enter the formula to get our final x sub 4, which I have as 3.755671965. And so this number is an approximate solution or root to this equation. If you plug this number in for x, the two sides of this equation should be very close to equal to each other. And so that's pretty cool, because this equation, you know, I don't know if there's an algebraic technique to solve this equation. Like, you can't just add something to both sides to get x by itself. It's not a basic algebra equation. So how do you solve it? And this is a great technique to get us an approximation, and we can make it as precise as we want, given the limitations of the computers that we're using, or calculators that we're using. So those are several examples of Newton's method. I hope you like it. It's really cool. Play with your calculator, become proficient, and enjoy.